Good day, students. So in this group, we're going to be going over an example where we're going to be finding the derivative of a function by applying the properties of logarithms, okay? All right, so before we take a look at the example, let's do a real quick review on the properties of logarithms, okay? So review. The three properties I'm going to go over today are the product, quotient, and power property, okay? All right, so the first one is the product property. Product property. So let's say you have log base b of two factors, x times y. This can be written as log base b of the sum of the factors. So it's log base b of x plus log base b of y. Okay, so if the argument of the logarithmic expression is a product of two functions, you can break it down and express it as a sum of the logarithm of the individual factors. Okay? All right, the second property is a quotient property. Quotient property. Now, very similar to this, but log base b, in this case, if the argument is a quotient of two functions, x over y, it can be written as the log base b of the numerator, or the dividend, minus, in this case, the log base b of the denominator, or the divisor. Okay? And then lastly, um, is the power property. Okay, power property is just a repeated application of the product property. You just basically have an adding the same thing multiple times, and we know that repeated addition is multiplication. So that's what's happening here. So let me write it down for you first. Maybe you can see the connection or recall how it's connected. Log base b of, let's say, x to the y. Okay, this can be written as the power multiplied by log base b of the base. Okay, so x to the y is like x times x, y times. So if you want to use this product property up here, if you break it down, it will be log x added to itself y times, and the same is the same thing as y times log base b of x. Okay, all right. So this is an offspring of this one right here, property one. All right. So let me just give you a sub example. What if you were to expand this expression, log base b of, let me just make an example. How about have uppercase A to the third, B to the fourth, divided by C to the fifth. Okay, log base b of this expression, you have to expand it. Now, in this case, you notice that we have a combination of all the properties here. We have the product in the numerator, we have a quotient, we have a denominator here, and they're all powers. So we're going to be making use of all three properties here. So if I wanted to write this in expanded form, applying the quotient and product properties first. So I'm going to have log base b of a to the third plus log base b of b to the fourth, applying the product property to the numerator, and then to the denominator minus log base b of c to the fifth. Okay, now I can now apply the power property and power down all the powers of these, the arguments of the logarithmic expressions. So we're going to have 3 log base b of a plus 4 log base b of b minus 5 log base b of c. Okay, so that's just a real quick review on properties of logarithm. Now let's go ahead and do the example on differentiation, which will require the application of these properties, okay? So example 1, find the derivative of the function, the natural logarithm of x to the fourth times 3x plus 1 square over 2y minus, I'm sorry, 2x minus 1, 2x minus 1 to the third. Okay? All right. So let's take a look at this. So I want to find the derivative of that. Now, assuming I don't want to use properties of logarithm to simplify this. If I wanted to use if I wanted to use the quotient rule and the product rule, that would be very, very complicated to execute if I wanted to use that. Um, Let me set it up for you. Okay, if I wanted to use the product rule, which is not advisable, and the quotient rule here, what I'll do is I'm going to say, oh, I want to find ln, the natural logarithm of x to the fourth 3x plus 1 square over 2x minus 1 to the third. Now, I'm going to call this numerator u and call this denominator v, okay? So I want to take the derivative of that. So if I want to do that, first of all, I'm going to use the chain rule on the whole function. So it's going to be basically the reciprocal of this whole thing. So it's going to be 2x minus 1 to the third divided by x to the fourth 3x plus 1 square. Okay, that's the derivative of natural logarithm, which is 1 over x. And then I'm going to apply the quotient rule to this expression, okay? So the top is u, and the bottom is v. You know what the product rule is, right? I mean, the quotient rule is vu prime minus uv prime over v squared. So I'm going to have, this is multiplied by v, which is 2x minus 1 to the third, times u prime. So if I'm doing u prime, I have to use the product rule, right? So it's going to be, let me just bore you with this. Let me just show you. It says x4 times 3x plus 1 square prime. Okay, so this is u times v prime, and then minus minus u, which is x to the fourth times 3x plus 1 square times v prime, 2x minus 1 to the third prime, and then that whole thing divided by v squared. Okay, 2x minus 1 to the third square. Okay, what does this look like? This looks like a total mess, you know, to execute. Although it's doable, but it's a complete mess. If I wanted to use if I use the properties of logarithm, this problem will be much easier. Okay, so let me show you how to do it. So instead of jumping into the chain rule and then the quotient rule and then the product rule, I'll just rewrite this using the properties of logarithm. Okay, so I want to rewrite the problem, natural logarithm of x to the fourth times 3x plus 1 square over 2x minus 1 to the third. So let me cross this. This is a mess. Don't do this, okay? So, all right. So I'm going to write this as, first thing I'm going to do is I'm going to apply the quotient and product properties of logarithm, okay? So to the numerator, I'll apply the product property. So it's going to be natural logarithm of x to the fourth plus the natural logarithm of 3x plus 1 square, okay, minus the denominator, which is the natural logarithm of 2x minus 1 to the third, okay? Now I can further apply the power property of logarithm. And this one is going to become 4 times the natural logarithm of x plus 2 times the natural logarithm of 3x plus 1 minus 3 times the natural logarithm of 2x minus 1. Those look much nicer, easier to differentiate, absolutely. And when we do the derivative, you see the beauty of this function. So the derivative of this natural logarithm of x to the fourth times 3x plus 1 square over 2x minus 1 to the third. So the derivative of this whole expression prime, remember that the derivative of natural logarithm is 1 over x, right? So this is simply going to be 4 over x, okay, plus, and then the same process here will be 2 over 3x plus 1, but applying the chain rule to the derivative of the denominator, times, let me just put it here so you don't get confused, 3x plus 1 prime, okay, you have to use the chain rule here, minus the same story here, 3 over the natural logarithm of 2x minus 1. That's the natural logarithm there. It's just 3 over 2x minus 1. Okay, because the derivative of ln u is 1 over u. And times the derivative of the denominator 2x minus 1 prime. Applying the chain rule, since this natural logarithm has a function as its argument, so it's a composition of two functions here. Alright, so just simplify this. This becomes 4 over x plus, if I differentiate this using the power rule, it's going to become 3 times 2 is 6. 6 over 3x plus 1 minus, if I differentiate this, it's just 2 times 3 is 6 over 2x plus 2x minus 1. And there goes your answer, really nice and quick. Instead of doing the product rule and the quotient rule and all that stuff, it's not necessary. So sometimes applying the properties of logarithms can make the determination of the derivative extremely easy. Okay? Alright, so there you have it. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And you can post a comment to let me know what you think about this clip. More clips can be found on math.serve.com. Thanks again and have a wonderful day.